Well, first of all, I would like to thank the organizer of this conference for giving me a nice possibility to present here our recent results on the theoretical study of magnetic properties of nanostructured materials, like polymeric complexes of transition metals. I would like to say that these compounds attract much attention for application in multifunctional spintronic devices, nanoelectronics, due to their ability to switch between different spin states, given external stimuli such as electromagnetic field or strain. Electric, magnetic field or strain. In addition, at least hypothetically, the sensitivity of these nanomagnets from the chemical point of view to a change of chemical surrounding, for example, due to the absorption of small molecules on the surface, yes, can be used for the design of new magnetic chemosensors. Here you can see the main building of our, okay, let's put, this is main building of our university, you can see here, okay? Let's move to another presentation. Okay, this is my title, Kharkiv National University, and my collaborator is Vladyslav Cheranovskii from the Department of Theoretical Physics. In my talk, in our report, we will consider truly spin ladder models for some polymeric transition metal compounds and demonstrate the usefulness of simple valence bond idea for the search of not obvious relation between their magnetic properties and model parameters, effective spin coupling constant mediated by chemical structure. So it will be useful for targeting design of new magnetic materials for experimental work. The outline of my talk is here. First, I would like to say some words about spin formalism of valence bond theory of quantum chemistry, effective spin Hamiltonian approach, which is very popular in quantum theory of solid state, the quantum physics also. In contrast to mean field theory like Hartree-Fock or standard DFT methods, which are popular now in chemistry, quantum chemistry, the above method is many electron one, which works more adequately in the case of strongly correlated electron system, like nanostructured polymeric compounds of transition metals. Especially, it is important for adequate description of magnetic properties, because it's cooperative properties of above nanomagnets. Second, we consider briefly known relations between topology of spin lattice model and the ground state spin of this model. Here we presented some real existing polymeric compounds having macroscopic ground state spin. So, real ferrimagnetic molecular magnet, real molecular magnets. Finally, we present our results related to the analytical and numerical study of the energy spectrum and peculiarities of magnetic properties of mixed spin two-leg ladder model with decorated runs published this. In particular, we will consider in detail the possibility of the appearance of intermediate plateaus in field dependence of magnetization, definitely at low temperature, and the effect of spin anisotropy on magnetization profile of so-called Heisenberg-Ising mixed spin ladder model, which is of interest for the adequate description of the compound with strong spin orbital coupling. For example, for compounds of rare earth metals, complex compound of rare earth metals. Okay, let's move. Here, let us show, I would like to give short consideration of the effective spin Hamiltonian approach. What does it mean? In traditional method of quantum chemistry, valence bond theory, each covalent chemical bonds corresponds to pair of electrons with opposite direction of their spins. It's standard approach from textbook of our students. For example, for pi electron system of molecular ethylene, yes, 2 to both here. It's a carbon atoms, carrier of magnetic moments, and pair of pi electrons, and we have double bonds between two atoms, carbon atoms. And for this molecule, as you can see on this picture, we have two possible spin up, spin down configuration. Well, first one, second one, yes, and they are equivalent from the physical point of view. And the energy of such configuration is less than energy of the configuration with parallel spin orientation on the right side of our slide here. And it is known that interaction between two classical magnets, yes, is also minimum of such kind of interaction corresponds to opposite direction of this magnet. So it's such kind of consideration from simple valence bond theory is close to classical consideration of interaction of classical magnets, permanent magnets. From the quantum mechanic point of view, it is known that the energy of such interaction is proportional to scalar product of vector of the corresponding magnetic moment. It's follow from classical magnetic theory, and in quantum mechanics, the electromagnetic moments corresponds to Hermitian operator, capital S here, yes, and therefore we have here scalar product of this operator. If we have and we have such kind of consideration, Hamiltonian describing difference in energy of all spin configuration has such a form of scalar product, yes, this operator. This energy is proportional to coefficient G, coefficients of proportionality, which called coupling constant for such kind of interaction, for chemical bonds between two carbon atom here. This Hamiltonian was introduced in by Heisenberg in 1928, many years ago. Therefore, people call it Heisenberg spin Hamiltonian. Note also that this Hamiltonian can be easily extended to the case of more complicated conjugate molecules, molecules with conjugated chemical bonds, double and single bonds, yes, like pentadienyl molecules. 5 atoms here, 5 carbon atoms, for example, yes? And we have effective spin Hamiltonian of such a form, yes? Where summation go through 4, you can see here, 4 chemical bonds between 5 atoms. So index of summation goes from 1 to 4. We have some for chemical, some for all chemical bonds of this substance, of these molecules. Later, it was shown that covalent chemical bonds, yes, that covalent energy state of well-known molecular Hamiltonian like Hubbard model or Pariser-Parapol Hamiltonian of quantum chemistry with 1 electron per atom can be studied with a good accuracy by means of Heisenberg's spin model with appropriate parameterization, appropriate choice of coupling constant G. Okay. The result of calculations by this model are close to the results of full configuration interaction in molecular orbital theory, famous molecular orbital theory of quantum chemistry. And some references related to this matter are present here. You can see here different reference, different year, starting from 1928. Nevertheless, people attract big interest to this model up to present decades. Okay. Heisenberg's spin model also can be extended to the system of arbitrary value of localized spins. Here we have 1 electron, yes, but we may have to another atom, for example, nickel atom. Yes, we have two holes in electronic shell, and so total spin of such kind of electric shell of nickel atom, nickel plus 2 cation, equals 1. Okay, so differ from 1/2. And such kind of model can be extended, Hazen-Weisman model, to the case of arbitrary value of localized spin on the lattice. This permits us to study big family of chemical compounds with transition metal and rare earth compounds also. Very important that during such kind of study, in contrast, for example, to DFT theory, yeah, we use a small set of semi-empirical parameters, coupling constant, small set. And nevertheless, the result of simulation are rather good, adequate to experimental data. In solid-state physics, this parameter, coupling parameter, can be estimated by means of the comparison of result of theoretical simulation, for example, by means of equilibrium distribution, equilibrium partition function, like of the magnetic properties on the basis of corresponding spin lattice models, and non-experimental data. And we can extract from this comparison corresponding small set of parameters. And people say experimentalists, theoreticians also say that it's very important sometimes to use spin model with minimal set of parameters. If this model describes properly magnetic properties and, for example, another properties like temperature dependence of specific heat, spins, so-called spins part of specific heat. In this case, we can say that our model with minimal set of parameters describe catch adequately the main physics of our system. Okay, let's move another. Here, let us consider some example of class 1 dimensional system, the magnetic properties of which can be described adequately by effective spin Hamiltonian method. First one, here, first one, is a complex compound of copper, complex compound of copper. This is so-called isopropyl ammonium tetrafluoride cuprate. And here we have formula, chemical formula. Nickel, copper, isopropyl. This is known. It's this is chemical. This proper chemical formula. Isopropyl ammonium tetrafluoride. So here, and it is known. It's studied many years ago in 1981. Corresponding results of corresponding study are published in Physics Lattice, and such kind of compound has a property of molecular ferrimagnets. So it's actively with external magnetic field. And can be shown that the ground state spin of such kind of molecule, yes, is proportional to total number of unit cell, 3-side unit cell. If we have polymer, we have huge number of unit cell, so we have macroscopic value of ground state spin. And corresponding magnetic moment interacts strongly with external magnetic field. Okay. And what about copper? Copper cation here, copper 2+. This cation has one hole in d shell of atom, according to simple physics. Yes, and because of this, we have each copper atom is a carrier of spin 1/2. Yes, and according to simple classical theory or valence bond theory, we have opposite direction of neighboring spin. Yes, of neighboring spin, opposite direction. Yes, and in this case, what we will have, it can be easily seen that if we enumerate all atoms along the unit cell, all spin, side spin along the unit cell, Even spin and odd spin forms two subgroups, yes, with the interaction between or coupling of the spin, yes, is present only for the spin from a different group. So we have so-called the bipartite magnetic sublattice in this case, yes, or alternated spin system. For each 3-spin unit cell, we have total spin 1/2. No, spin up, spin down, spin up. Yes, so total spin 1/2. And it can be easily seen that the lowest energy state of such kind of lattice, spin lattice, people call it necklace ladder, yes, is proportional to total number of unit cells. So it has macroscopic ground state spin. Actually, such kind of consideration from the simple valence bond theory or from classical consideration of magnetic interaction is approximate. Yes, we have microscopic. We should consider this is molecular structure, so nanostructure. We should apply quantum mechanics because in classical consideration we did not take into account spin fluctuation. Nevertheless, final result is correct for quantum spin model. If you put here or such kind of Hamiltonian, it can be proved that ground state spin corresponds to this value, so not microscopic. Actually, this is particular case of famous Leibniz theorem, which can be proved on the basis of known Perron-Frobenius theorem of linear algebra. So, I would like to say that according to the sentence of one of my teachers, some obvious physical results can be proved mathematically. Yes, that's right for this purpose. And because of this, very unusual results, we have polymeric complex of transition metal with macroscopic spin, with properties of molecular magnets. And we can find these properties and prove it we can prove these properties to apply effective Heisenberg spin model and prove we obtain quantum mechanical proof that it's really real molecular magnets. And definitely such kind of result coincide with experimental data. Okay. Let us now consider another second example of these compounds with macroscopic ground state spin. This is nickel copper polybisoxamate hydroxide, yes? And such kind of here you can see big green balls corresponds to the spin 1. Yellow balls corresponds to spin of copper nickel, yes? And therefore, for unit cell, to site unit cell, for example, we have non-compensated total spin. And in the result, it can be easily seen that we have macroscopic spin for the ground state, according to Leibniz theorem. But I would like to say that in this case, original Leibniz theorem corresponds to spin 1/2. But there is some expansion of Leibniz theorem proved by Professor Douglas Klein. And by means of this extension, we can consider arbitrary set of alternating or bipartite spin lattice with arbitrary spins on the sides, corresponding to the size of this lattice structure. The main idea, the corresponding magnetic sublattice should be bipartite or alternated. Here, on the left side of our slide, the real monostructured bimetallic magnetic materials having 2D magnetic sublattice, like square lattice, yes, or rectangular lattice, is present. This sublattice is formed by, this is for chemical formula of this compounds, yes, and this compound has 2D two-dimensional nanostructured materials and just show magnetic properties. So it's molecular magnets also. We can consider it like two-dimensional magnetic materials or nanomagnets. Okay, and we have here nickel and iron atoms. For example, here we have a nickel +2 spin 1 yellow ball, and blue balls corresponds to foreign 3+ cation, S equals 1/2. It's a bit smaller in our in comparing to the size of nickel, because spin is bigger. So we have such kind of structure. Okay, it's proposed in this work. In this work, I found the data related to magnetic structure and magnetic properties of such kind of two-dimensional magnets, nanomagnets. And on the right slide, on the left, okay, on the right side of our slide, yes, you can see hypothetical tubular structure formed by rolling up a fragment of square lattice, left square lattice, yes, with wides and small wides and length L, where L much bigger than L. So we have some kind of nanoribbons, yes, non-carbon nanoribbons, and rolling up it, and roll up it. After that, we obtain tubular structure, non-carbon nanotubes, for example, of such a way. And we have different coupling parameter between carbon atoms between iron and nickel atoms, because of in the result we have some distortion of chemical bonds, the distance between carrier of magnetic moments. Okay, and definitely we have surrounding. We have here we have some kind of ligands, yes, cyano groups, and fluoride, yes, also. So we have some kind of non-direct magnetic interaction between carrier of magnetic moments through the another group, cyano group, and propan diamine also. Diamine, it's organic molecules, organic ligands here. Okay.
And
we have such kind of structure.
From
the theoretical point of view, it would be nice that this spin model, such kind of. So, as for this, it's because it was only introduction in my in my consideration. Okay, but I would like to say that such kind of nanotubes have microscopic spin. You can see here, we can find such kind of estimation for spin, and in our work we consider magnetic properties of such kind of nanotubes and propose to use it as a magnetic nanocontainer for targeted delivery of drugs mediated by external magnetic field. Okay, let's move on. I don't wish to spend more time for this, please. Okay. Thus, in the result, there is a wide variety of magnets with quasi-one-dimensional magnetic sublattice of various structure. Therefore, the theoretical study of model spin lattices with unusual properties is significant, has a significant interest for the targeted search of nanomagnets. From the theoretical point of view, it would be nice to consider spin models which much more simple structure, but which demonstrate peculiarity of magnetic properties. From this point of view, let us consider much more simple model, so-called two-leg spin ladder model. There is really existing compounds having such kind of magnetic sublattice, and we have here carrier of magnetic moments of copper cation, yes, carrier of spin 1/2. And how we can, but as for magnetic properties of this model, we have no big interesting features, and therefore we should perform some modification of such kind of simple two-leg ladder models. How we can do it? First of all, we can do it by introduction of a diagonal interaction. This means the simplest way, yes? Introduce next nearest neighbor coupling constant, yes, here. This right-handed ladder model permits us to study in detail possible quantum phase transition using Mazin-Lamgosh idea of from famous work, this famous work in Journal of Mathematical Physics. Okay. Another way to modify our two-leg spin ladder model is to consider two-leg spin ladder with decorated legs. Yes. In this case, if you have decoration, if you for first leg we have total spin proportional to the difference between S1 and S2. S1 is first spin, S2 second spin, and we have isomeric. So no, we can study it in our work here last year, and magnetic properties, and demonstrate such kind of model demonstrate intermediate plateau in field dependence of magnetization and at low temperature, and isomeric structure. Consider this 8 spin per unit cell, isomeric structure. Such kind of structure. This is unit cell, yes? Not here, this is 6. Sorry. Control Z. This is, this is unit cell. More complicated unit cell, but it's less interesting case because total spin equals 0. Nevertheless, for first ladder, we can show that existence of intermediate magnetization plateau. For second ladder, such plateau is absent. And now let's move directly to our two-leg spin ladder, another case, yes, with decorated rank. A bit more simple model from the theoretical point of view, but this simple model permits us to consider its property in details, yes, to apply different methods of quantum mechanics, the quantum theory of magnetism. Okay, the corresponding Hamiltonian has such a form. Okay, here S dash, this is operator for spin, which has S dash here. So the spin in general case more or less than 1/2. So it may differ from spin S. And we take into account the structure with spin S equals 1/2. So blue balls correspond spin 1/2, and these balls, yes, red balls or crimson balls corresponds to spin S dash. H here is external magnetic field in energy units. Okay. Let us first consider weak interaction between decorated ranks. In this case, we can apply perturbation, first order perturbation theory and obtain effective spin Hamiltonian of such a form. Okay. Using exact result for Heisenberg spin uniform spin 1/2 chain, we can obtain estimation for energy of infinite chain. We have such kind of estimation. Okay. After that, we can consider maximum. If we have here according to this description, first order perturbation theory, we have spin 1/2 effective Hamiltonian with such kind of coupling constant was over 8 G1. Yes. In this case, we can find maximum spin of this spin 1/2 ladder is proportional to A. It equals A over 2. Okay. Minimum energy is corresponds to total spin which equals 0 according to Lib-Schultz-Matisse theorem. Okay. In the result, if you consider minimum or such kind of minimal energy with a parallel orientation of effective spins, yes, of unit cells, and minimal energy corresponds to A equals 0, we can obtain the estimation for difference between such kind of state, and we can obtain estimation for applied magnetic field, yes, at which this magnetic field, critical value of magnetic field, corresponds to change of spin state of our system from the 0 spin to total spin, which equals L/2. So all effective spins are parallel in the result of act of external magnetic field. And such kind of minimum value of this magnetic field, critical value, has such a form. Approximately 1.33 G1, quantity G1. We can consider also excitation with total spin L/2 plus 1. What does it mean? This means that one of the unit cell has total spin not 1/2, has parallel orientation of spin. So we have 3/2 spin. Definitely, in this case, difference in energy should be proportional to G2, which much more bigger than G1 if we use perturbative treatment. Now, according to this treatment, I would like to skip some words and some details. We can obtain next critical value of magnetic field, which corresponds to the end of intermediate magnetization plateau. Because if we have energy gap between state with total spin S equals 1/2, yes, L/2. So spin per unit cell equals 1/2 in this case, yes. And we have such kind of state, and we have energy gap between the state. We should apply external magnetic field to overcome this energy gap. And in the result, we have two critical fields, which corresponds to the beginning and the end of corresponding intermediate magnetization plateau. Okay. To check our consideration, adequacy of our perturbative consideration, we performed exact generalization study of finite cluster formed by 12 spin for such kind of model, for above model. This means we use exact generalization study to obtain all exact energy state for our cluster, yes, cluster of 12 spin, and after that use partition function, standard Boltzmann distribution, and obtain corresponding estimation for magnetization per spin. Maximum magnetic moment per spin equals 1/2. This means we have fully polarized state here, yes? And we have intermediate, you can see here, intermediate magnetization plateau. From the beginning, in the absence of magnetic field, we have zero magnetization, and after some initial effective field, you can see here such kind of field, 1 point and something else, yes? So very close to our estimation. And we have another critical field after which corresponds to the end of this plateau. And we can consider G2, coupling G2, which equals 1, no magnetization plateau, 2, small magnetization plateau, and 4. So the size of magnetization plateau is proportional to coupling constant in ranks. We have such kind of conclusion. And in order to check this conclusion by means of consideration of big clusters of our spin ladder structure, we applied DMRG, the density matrix renormalization group estimation for critical fields related to intermediate plateau. And you can see such kind of, we used such kind of parameter and 40 optimized state. It's a standard 4-block scheme for DMRG calculations. And if you consider 202 unit cells, that's 100 step of DMRG calculations, yes? In this case, we have such kind of relation between, you can see here, a coupling constant G2 in ladder, yes? Between coupling constant G2 in ladder ranks and critical magnetic fields, H1 and H2. You can see here that H1, first critical field, does not depend on the value of G2, according to our perturbative treatment. But second critical field, G1, increase linear dependence with the increase of value of G2, which also coincide with our perturbative treatment and finite and previous, you can see here, bigger size of magnetization plateau, when we increase value of G2 and previous calculation. So we have full agreements of such kind of consideration. Let us, I would like to skip some details again. Let us consider the case S pi prime bigger than 1. Yes, S equals 3/2 in this case. In this case, similar consideration leads to our effective Hamiltonian. And we can say that according to Haldane suggestion, physical letter, famous Haldane suggestion, if S, this spin, yes, so if we have S dash has integer value, in this case, we have 0, we have, for example, S dash equals 1. In this case, we have 0 here, yes, from the first order perturbation theory. If S equals 2, we have S effective spin, which corresponds to total spin 1. But in this case, we have energy gap between ground state and excitation. So we have 0 field, 0 value magnetization plateau, yes, for such kind of, for effective spin, our spin dash, which takes integer value. If the spin takes half integer value, we have 2 magnetization, intermediate magnetization plateau, non-zero magnetization plateau with magnetic moment per spin, which corresponds to S dash minus 1/3 and such kind of value also. Okay. And let us consider the corresponding exact derivatization study the result for magnetization profile. We have similar picture for the spin S1/2. And you can see here, it's such kind of the intermediate magnetization plateau, which corresponds to the spin, total spin S prime 3/2 minus 1, yes, 1/2, 1/6, yes, 1/6. You can see here, this is 1/6 magnetization plateau. And for big value of G, we have second magnetization plateau, which corresponds to total spin. You can see this formula. If S equals 3/2, we have M equals 1/2. Okay? So we have 1/2. We have 1/2. So we have 2 magnetization plateau for our spin model. And finally, I would like to finish my consideration. Let us consider comparison of magnetic profiles of anisotropic and isotropic spin ladder clusters formed by nine spin. Okay? In this case, if we skip a detail of this consideration, this exact diagonalization study also. The main idea, the main result, which corresponds to such kind of consideration, is that in contrast to isotropic spin ladder, the model with ion interaction in ranks has only one intermediate magnetization plateau. And such kind of consideration definitely coincide with, we can consider also corresponding perturbative analysis, and which supports this conclusion. So this means we have interesting results, because usually anispin and isotropic produce more complicated magnetization profile. In our case, magnetization profile, blue line, simplify in comparison with Heisenberg spin model. Okay? So we acknowledge support by IEE, that's Institute of Electrical and Electronic Engineer, yes, via Magnetism in Ukraine initiative. This is such kind of small support, but valuable support, and we acknowledge this support. This for Ukraine, Magnetism for Ukraine, such kind of program. Okay. Thank you very much for our consideration, for your attention. If you have any questions, please ask me. That's all. Here, main building, main square before our building, main university building. This is Square of Freedom right now, or Svoboda Square in Ukraine.
Thank you.